Hello and welcome back everyone. In this video we're going to cover section 6.2. We're skipping all the way ahead and learning how to solve trig equations. And there's going to be three types of problems that we're going to look at. As you can see, the first type is when you have a trig function with just a variable, of just a variable equals a number. And then you're going to have a trig function applied to an expression equals a number, so just a little bit more of a generalization of type 1. And then type 3 is kind of totally different, and we'll get to that near the end of the video. In the meantime, let's talk about types 1 and 2, and I'm going to recommend having your unit circle and that chart full of trig values on it, since it'll be helpful in solving problems like this. Okay, so let's suppose we have a trig function, so this is one of the six, so sine, cosine, tangent, cosecant, secant, cotangent, right? And then you just have the variable, so it could be theta, it could be x, it could be t, as long as it's just a variable, and it equals a number. So what you're going to do is look on that chart or look on the unit circle and find within one lap of the circle, well, actually it depends on the trig function, but essentially you're going to find all possible angles that give you that number when you plug it into that respective trig function, and then you're going to get all possible solutions, add the appropriate multiple of the period, so either pi or 2 pi. So let's do part A. I know this is all very abstract. So what you're going to do is go to the chart and look down the tangent column and find all of the angles that have output square root of 3. And if you see, I think theta, the first angle for which this is true is pi over 3, if I'm not mistaken. And now you'll notice you can skip down farther and you'll see that also angle 4 pi over 3 is another one. But here's the thing, with tangent and cotangent, you only need to look at the top half, so from angle 0 to pi, because we know that tangent and cotangent repeat themselves every pi units. So really, just looking at the top half, there is only one angle, in particular pi over 3, that gives us the correct output, right? And so now, what this second bullet means right here is, since we know the period of tangent is pi, we then add to this pi times n. And now where n is an integer. And now think about it. What if n were 0? Well, then you just get pi over 3. Check, that one works, we know that. If n were 1, then you would get 4 pi over 3, which we know also works, right? And then if n were negative 1, you would get minus 2 pi over 3, which you can show also works. So this captures all possible solutions by adding on the period times n, okay? So now coming down here to part B, let's look at sine. So now we're going to look in the sine column, and you'll notice, or if you'll recall, sine has period 2 pi, so we're going to need all angles on that whole chart in the sine column that give us an output of 1/2. So theta equals, well, what's the first angle for which that's true? I think it's pi over 6. And then also theta equals, what's the next one? I think it's 5 pi over 6, right? And now sine repeats its values every 2 pi units, so I just need to add on to here 2 pi, which is the period, times n, and then also here for 5 pi over 6 plus 2 pi n. And I encourage you to check, like, what if you took 5 pi over 6 and added, let's say n were 3. What if you added 6 pi to 5 pi over 6? Well, that corresponds to essentially finding angle 5 pi over 6 and then going 3 more times around the circle from there, which essentially lands you back in the same place, right? And so you can say where n is an integer. Now coming here to cosine, go ahead and try this one on your own. Look down the cosine column. You'll need all angles in this chart, we'll call them t, that spit out -1 when you plug them into cosine. So the first one is pi. And that appears to be it, right? So all you would do is just say pi plus 2 pi n, where n is an integer. And if it helps to think about this one, here's the unit circle. Here's angle pi right back here. The cosine of which is -1. And so if I add any multiple of 2 pi to this, you notice I'm always ending up back at the same place, right? Because adding on 2 pi just means go a lap around the circle. Okay. And that's the same for all of these other ones up here. So if you like, you can put a box around them, circle them, whatever you prefer. Okay, now type 2, we're going to do pretty much the same thing, only now we're going to have expressions, right? So look in the cosine column, find all angles that when you plug them into cosine give you a value of 0. So the first one, whatever 2x minus pi over 4 is, it has to equal, well, angle pi over 2, right? But we know that since cosine repeats its values every 2 pi units, we do a plus 2 pi n. Now there'll also be another solution here. If you look further down the chart, you see that 2x minus pi over 4 can also equal 3 pi over 2. And now we know because cosine repeats its values every 2 pi units, we add on a 2 pi n. Okay, so now, so that's what the solution says here. It says repeat essentially the steps for type 1, but now solve for the variable. So we need to solve for x in both of these equations. So I'm going to add pi over 4 to both sides. So I get 2x equals 3 pi over 4 plus 2 pi n. And I'm going to divide both sides by 2. And so I get x equals 3 pi over 4 plus 2 pi n all over 2, which is 3 pi over 8 plus pi n. Now do the same thing here. So we get, if you add pi over 4 to both sides, you get 2x equals 7 pi over 4 plus 2 pi n, and then divide everything by 2. So you get 7 pi over 8 plus pi n. Okay. Now try this one. Find all angles in the sine column. Going down the full chart, you're allowed to go the full chart for sine and cosine, and secant and cosecant. For tangent and cotangent, remember you just use the top half of the chart. But okay, so go down, and what do we get? We get that 4x minus pi over 4 can equal pi over 4 plus 2 pi n, or 4x minus pi over 4 can equal 3 pi over 4, and then plus 2 pi n, right? And those are the only two angles within one lap of the circle whose sine value is root 2 over 2, okay? Now we just solve for x. So we add pi over 4 to both sides. We get 4x equals pi over 2 plus 2 pi n. Divide everything by 4. We get x equals pi over 8 plus pi n over 2, right? So this is one of our answers. And now same thing over here. Add pi over 4 to both sides, so you get 4x equals pi plus 2 pi n. And then divide everything by 4, you get x equals pi over 4 plus pi n over 2. And if you want, I've been sort of neglecting, but it's assumed that n is meant to be an integer. So of course you can say where n is an integer, but unless otherwise noted, especially given the context of these problems, I'll know that you mean n is an integer, okay? All right, now coming down here to type 3, you kind of have to use some algebra techniques to solve these problems. So here, looking at this first one, there is no set rule to solve this. just kind of follow your nose here. So for something like this, maybe isolate cosine of t. So you'll notice 2 cos t equals -1, and then I can divide by 2. And so cos t has to equal -1/2. Ah, but now this is a type 1 problem, right? So look down the cosine column. You're allowed to use the full chart. Which values for t, which angle values, give you an output in the cosine function of -1/2? Well, that's 2 pi over 3. And again, remember, because we're dealing with cosine, you add plus 2 pi n. And then there's also, I think, one more. What is it? 4 pi over 3. And again, add 2 pi n. And that's it, right? You've already solved for t, right? So that's all there is to it. You just get these 2 groups of solutions. Okay. Now coming here, it's a little bit different. Think of this like a quadratic, right? This is technically a degree 2 with regard to tangent, right? And how do you solve quadratics? You move everything to one side and factor. So the way I would do this one is I would say this is tan squared of x minus 1 equals 0. And now notice you can factor this. This is tangent of x squared minus 1 equals 0. That's what this notation means, right? And so you have a difference of squares. Well, go back to high school algebra. This is tan x then plus 1 multiplied by tan x minus 1. Right? And so you were able to factor this. Well, that tells you that tan x can be, well, if you look here, tan x can be -1. And also tan x, if you look at this second one here, well, tan x could be 1 as well. Right? And so if tan x equals -1, only use the top half of the chart. What does x have to be? Well, let's take a look here. I think x has to be 3 pi over 4. And now do I add pi n or 2 pi n? Right? Tan repeats itself every pi units, so you do plus pi n. And now let's look here. Where does tan x equal 1? Well, only use the top half of the chart. I think right at x equals pi over 4. And that's it. Notice the variables are already solved for, so there's nothing really much else to do there. All right, looking at this one here, pretty much do the same thing. Move everything to one side because technically this is quadratic in tangent, right? And now you can factor, right? You can factor out a tangent x, and you're left with tan x minus 1. Okay, so this one says tan x can be 0, or tan x minus 1 can be 0, which says tan x equals 1. Oh, this one we already did, right? That's x equals pi over 4 plus pi n. So that one we know is good. But now look here, where does tan x equal 0? Well, that's exactly when x equals 0 and then plus pi n, right? And so what I would recommend is you don't need to write the 0, right? That doesn't contribute anything meaningful. And so x equals pi n is good enough. And you may be thinking, well, wait, tangent also equals 0 when x equals pi. Yeah, you're right. What if n were 1 here, right? That captures x equals pi times 1, which is pi. So try this one. Notice it's quadratic in sine. We should be able to factor this as sine theta, let's see, plus 3, sine theta minus 2. This one says that sine theta plus 3 has to equal 0. This one says sine theta minus 2 has to equal 0. So we get 2 equations. One is that sine theta equals minus 3, and the other one sine theta equals 2. Okay, you're going to look down your column of sine values, and you're not going to find any angles for which this is true, nor will you for this one either, right? So in fact, there are no solutions here. And here's the reason why. Sine only outputs numbers between -1 and 1. It doesn't spit out any numbers that are less than -1, like -3, or bigger than 1, like 2, right? So this equation here has no solutions, just based on the properties of sine, not spitting out numbers less than -1 or bigger than 1. Okay, now let's come down here. Notice this is quadratic in cosine, so this should factor. Go ahead and try it. Notice you're going to keep the 2t, so this is cos 2t minus 2 and cos 2t plus 1. Okay. And so this equation that we get from this one says that cos 2t minus 2 equals 0. This one says cos 2t plus 1 equals 0. So the first equation can be rewritten as cos 2t equals 2, and the second one can be written as cos 2t equals -1. Okay, look down the cosine column. Does it ever happen that you're ever going to get a value of 2 as an output of cosine? No, right? For the same reason as sine, not ever equaling 2. The cosine does not spit out values bigger than 1 or less than -1. So just this part right here has no solution. But I think this one does, right? Look down the cosine column. Which angles spit out a value of -1? Well, it looks like pi, right? So in this case, we would say 2t equals pi. And now remember, cosine repeats its values every 2 pi n. And now just solve for t. So t equals pi over 2 plus pi n. And so while part of the, it's kind of like with logarithms, right? Like part of the problem may have no solution, but another part will, and so that's the only one that you keep. Everything else you reject, right? Okay, so hopefully this helps you with the worksheet, the second worksheet for this week.